Good morning, Jan. Good afternoon.
Michael, good morning at your side.
Good to see
Just
you,
in
sir.
time.
Yes, indeed. Yeah,
How are you doing?
very good. Very good indeed. And
I
we have
think Caden.
Caden.
Hi,
Hello,
Caden.
hello.
Hello. Good morning. Good evening to you.
Good
How are you doing?
evening.
How have things
How
been
are you
going
doing,
this
Caden?
past week?
Wait a minute. Let me adjust my microphone. Wait.
Yeah, we
Okay.
can hear you just fine.
Okay. So sorry. What did you say?
Yeah, just how have you been this past week?
Yeah, it's been a little bit hot here since the summers begin.
Hmm.
Yeah, the temperature can go to like 33 degree. Yeah, pretty hot.
Hmm.
Yeah, indeed. Yeah, we're feeling a bit of a heat wave here in Texas as well. So, um, I let's see, Alexa, what is 95 degrees Fahrenheit in Celsius?
95 degrees Fahrenheit is 35 degrees Celsius.
Yeah, 35. So it's
Wow,
Whoa,
it's pretty hot as
yeah,
well.
yeah. I
that's
should I should really figure
just
out how to do that conversion in my head. I can almost
Yeah,
do UTC
that
conversions in my head now.
yeah. So it's even hotter over there than it's here for the moment.
Yeah, for the moment.
yeah.
But okay.
Yeah. Well, yeah. This morning I've got some updates on Janaga.js, the query engine.
Hmm.
So I definitely want to go through those. Yeah, what else have we got on the docket?
I have some the test procedure for the loading. The loading is not yet finished, but the testing is okay, I think. And remember that a few sessions ago I asked you about the prototype and the runtime facts.
Mm-hmm.
I forgot it again, but now I worked out how to get from one to another, all the different. And I would like you to have a look at it, but perhaps start with
Okay.
what you found out.
Yeah, let's do that real quick. So, this is the screen number 2 live. Okay. All right, and then now I think everybody is seeing that
Yes.
there. All right. So, so first of all, a quick review of the starter model. So this is the application that is built into the starter kits. So here's starter TypeScript React, and so it's got visits. So you can record a visit to a domain, and that's a visit by a user. And then on the user side, you're recording the user's name because they log in as it ships by default using Twitter. So that produces this model. And so what I would like to be able to do is, starting from the domain, give me all of the visits. Okay. So let's flip over here to the branch in Janaga.js where I am working on the new query engine. And so here is the specification for the query to get all of the visits. So given a domain, which is a myapplication.domain, match visit, myapplication visit, where or such that visit domain being a domain is equal to the domain that is given. So just find all of these successor visits. So the last time that we looked at this, the interactive application was showing you the SQL that would be executed, as well as the parameters for that SQL. But now, if I run interactive, it is actually executing that SQL. npm run interactive, yeah. npm run interactive. There we go. Now it's actually executing that SQL, and it is giving you back a collection of tuples. So each tuple has just one fact in it, and that fact is the myApplication.visit, and here's the hash of that fact. So after this, the client application would call load, and for all of those hashes that it does not yet recognize, and it will get the actual fields and predecessors and everything in order to reconstitute those particular facts. So a few things to point out here. This is giving you back an array, and this is an array of streams. So the specification is nonlinear in that it can branch. It can have multiple matches here, and it can also then do the existential queries, and each one of those existential queries also produces a separate stream. And it can also do projections. So if we do the arrow syntax at the bottom, we can then specify a projection. And so we talked about those parts of the query language last time. But all of that means that that this doesn't just produce one single stream of tuples. It creates several different parallel streams. So, for example, if we had some kind of an existential condition that on a visit, so somehow a visit could be deleted, could be rescinded. I don't know. The fact that rescinds or deletes that visit would go in here, and you would have a path that joins that back to the visit. And so that would produce a tuple of visits where this thing does not exist, but then it would produce a separate stream, which is a tuple containing visit and the visit deleted fact. So that would produce two parallel streams. It has to be parallel streams because if it's in that second one, then it's no longer in that first one because it executes the existential condition. And then similarly, if we do a projection, then each element of the projection produces another stream for that subquery. So we can get a lot of streams going on in parallel. Ultimately, I see this as kind of like, let's take the entire user interface of the client application and let's merge all of those screens together. So so you start the application, and then in order to produce this this list that it shows at the beginning, it's got to to run a specification, and then it's got to do some projections on that in order to populate the elements of the list, and then it's got to run a different projection for like the username up in the corner, and then different projection for each of the different elements. So on the client side, we could actually merge those projections together, create one projection, send that to the server, and then the server knows all of the different streams that application is interested in. So we talked a little bit last time about how this language is computing interest. So that's a little bit more detail into how that happens. Then each stream is identified by the labels that are part of that tuple. So this one just has the label visit. If I were to, now let's go back to the model, and let's say that I want to grab the user for that visit. So I can say user is a Janaga user, and user is equal to visit user. Let me make sure that that's the correct name here. We've got visit user. Yep, that's the name of the role. That being a let's see, the user is a Janaga user. Yeah, and so the visit user is equal to user. So first of all, in this query specific, in this query language, this DSL, the label that you are introducing here has to be the one that appears on the left, and then the one on the right has to have already been declared somewhere else. So so it's constrained to make it to make it easier to for it to predict which is going to be on the left and which is going to be on the right. That's not a constraint when you're working in Janaga.net, for example. If you're writing a link query, it'll figure out which one should be left and right. But for this, let's use that constraint. So we save that, and oh, it errors. Cannot generate SQL. Okay, we have some issue going on there, but all right. So I'll come back and fix that that issue. But what that should have done is produced a stream that has the labels visit and user, and then the tuples that you find within that stream will be the visit fact and the user fact, and so those are listed in the same order as the labels there. So this is the really interesting part, and this is the thing that I was kind of hinting at last time, the bookmark. So if you think about what a stream is, it's a sequence of tuples where the elements of the tuple are facts, and the facts are the labeled components within this diagram. So we put a label on visit, we put a label on user, we might put a label on username, and so now we would, when we run that specification, given a domain, we would expect a sequence of tuples that contain facts of these three types. And so each tuple represents a possible walk through the graph. So the visit that's in that tuple actually does point to that user, and that username also points to that user. So that's a possible path. It satisfies all the constraints. The order in which these things happened is a little bit undetermined. So the username could have been changed after the user visited the application. So the username fact might have occurred later than the visit, or it might have occurred before. So they log into Twitter, and we know what their name is, and then they actually perform the visit, and so we've got the visit fact. So since the order between these two is undetermined, the stream might actually have some situations in which an earlier part of the tuple opens up a whole bunch of stuff that happens later. So in this particular model, you get a visit from a user who has changed their name multiple times. So prior to that visit, your stream might be empty. You might have already read up to the end of the stream, and then as soon as they visit, now you've got you now have interest in all of their usernames, because you're looking for all of the matching tuples, and so that means that the addition of one fact needs to open up an entire history of tuples within that stream. But conversely, it could have happened that they've already visited your site, and then they changed their name. The server learns about that, and so the server just has to put one tuple at the end of the stream, and it's the same visit that you had before, the same user that you had before, but now a brand new username. So the order of the tuples within the stream is not determined by any one particular member of that tuple. It could be any of them, and in fact, the order is primarily determined by the most recent tuple. So in that first example, it would be the visit. The visit was the thing that happened most recently, and now you're interested in all of their names. Or in the second scenario, the most recent is the username. So when that happens, you get just that one tuple. Then if you do have that first scenario where one brand new visit occurs and you get a whole bunch of new tuples, you still have to be able to order those relative to one another, because you need to be able to walk through that history in sequence in order to update your bookmark. And so the most recent tuple is only the primary order. The secondary order is the second most recent tuple. And then in this case, since we've got three, the third, the least recent tuple, member of the tuple. And so you have to order these. First of all, you take some monotonically increasing order of the facts within the tuple. You put those in decreasing order, and then you order the tuples themselves within the stream according to that collection of monotonically decreasing identifiers, or monotonically increasing identifiers. So the upshot is, so if we come back here, we see bookmark 4. This only has a single element because we only have a single label. If I were able to add a second label without that syntax error, then you would see something like 4.2. And then this would be 5.2 and 6.2. So this would say this is the visit from user identified by the number 2. And then the bookmark that comes out here at the end, this is the most recent bookmark in that stream. So if you get back an empty list of tuples, it's the bookmark that you started with. But if you get back this sequence of tuples, it's the bookmark of the last one. So the client saves its bookmarks per stream. So it sends that to the server, that specification. The server sends back a whole bunch of streams. Each has a different collection of labels, and so the client saves a bookmark per one of the per label or per set of labels, and then reads those tuples, calls back to get the actual to load the actual facts for those tuples, and then after it's done, all of those in that particular block of the stream updates the bookmark for that set of labels for that stream, and moves on to the next and the next and the next, and then it's got all of those streams up to date. So a lot happening there, but that solves some pretty significant problems. It solves the problem of, like, for example, if you hire a brand new employee, that's one decision, that's one fact. But now the fact that they are an employee of this organization, if you do a query, you have a specification that starts with the organization, and you want to have the list of projects and share that with every employee of that organization, then that one decision is going to open up a whole bunch of new facts for you. So recording a fact should not create a whole bunch of elements in a queue. It shouldn't on insert fan out and do a whole bunch of work. Nor should the client be expected to receive everything about this new hire all in one request. It should be able to batch those up. And so this solved that problem of being able to batch things up. Things that you weren't interested in the past because of a new fact, now you are interested. It's able to load those new pieces of information.
Cool.
Yeah. I wish the the continuation here had worked. This was the first time that I tried that, and I said, it should work just fine. Okay, it didn't work.
So this has been published to the Generica.js?
It is in a branch right now, so it's not been merged to main.
Okay.
But yeah, you can check out the projections branch, and that's got this code in it. So if you go through the process of creating a new project from one of these starters, and setting up a container using Generica Postgres, then you can just hit the application a few times, generate some data. So here I've logged in to a Twitter as Michael L. Perry, and hit refresh a couple of times, and generated some data there. And all of the instructions for starting the application using the starter kit, those are all in there. So yeah, just a few things you need to do. Like for example, in this case, since it is using Twitter, you need to register for a Twitter OAuth API key, and then it'll allow you to build applications that can log in with Twitter. So a few little steps there, and you've got the data, and then you can play around with querying the data.
That's pretty impressive. But so that means that actually all the data for one user screen, we can just load it with one single query.
Yes indeed. Yeah, and so yeah, if you think about the way that that we design APIs by hand, a lot of times we design the API for a particular screen. So we think about, okay, when they enter the screen, first of all, we're going to know who the user is because that's part of the header. So we've got that that coming in. Well, that's represented by one of the parameters here, and then we're loading this screen about a thing. They've navigated to some part of their application. So in this case, the domain is the thing that it's about. So that's where they've navigated to. They've just opened the browser and gone to that domain. And so then design the API to satisfy that particular client, and then oftentimes you'll say, well, I don't want the API to be so client specific, so I will try to design a generic API, and then the client has to make one API call to get a list of things, and then make other API calls to get the details about those things. Do all of this work, and then it can show something to the user. So things like GraphQL have come along to say, okay, let's let the client figure out what the data structure should look like, and that prevents the overfetching, that prevents all the latency of all these different round trips, so that you can just fetch the whole data structure and display it. So this kind of follows along that progression that GraphQL started. So the client gets to decide what the query looks like. But then it takes it one step further because it's got the bookmarks in there. And so now the client can just say, hey, give me what's changed since the last time we talked. So that supports the offline mode where now you save those bookmarks and you've already saved the data. Next time you launch the application, make the query, just get what happened from then. Meanwhile, you're showing the user the information that's in their local database, so it just starts right up. Doesn't wait for the API call to come back. Then, as it comes back, it updates its database, it updates the user interface, and you start to see the new data appear. Then this also supports the idea of having that connection be live. So you've got a WebSocket now. You've opened up the web, or you've opened up the WebSocket. You've sent that with the bookmarks, and then it says, okay, here's the data so far. All right, we're finished with that data stream, but we're going to keep the WebSocket open, and then as new things happen on the server, it pushes those to the client because they satisfy that specification.
Mm-hmm. So it can be used in a watch, in a J.watch.
Yes, exactly.
Okay, that's great.
Yeah, so I'm pretty excited about this. Just need to iterate on it and actually make it work in all the different scenarios. So make it work for more than one member of the tuple. Make it work for projections, for existential conditions, and so that's what I'll be doing over the next few iterations.
So for the moment, you just write your query in specification.txt file, and Interactive will automatically load that text file and execute the query.
Yes.
Okay.
Yes.
So that way we can play with it.
Yeah, and if we take a look at interactive index.js, so it's just doing Node.js, run this thing, and pipe specification.txt into it. It is starting from a particular fact, so it's starting from my application.domain, where the identifier is my application. So if you need to change the starting point, and also notice the starting point is an array now, so you can start from a tuple of facts, so that you can pass in this domain, this user, and you can see now within that context, what has this user done on this domain, or what is the user interested in. So these are all the projects that they're assigned to within that domain, and so send those in as members of that tuple. Pass in the bookmark, pass in the limit of the number of tuples that you want per stream, and the specification, and then just some of the parameters are hard coded, and then the specification itself is the one that comes from the input file. So maybe one day there will be an actual development environment or query environment where now none of this is hard coded. You get to say, all right, let's write my specification. Let's log in, and so now that's going to be the user object to use. Let's pick the domain from a list, and then instead of just showing you some hashes, maybe let's go ahead and do those loads and then show you a graph, or maybe just run those projections that are inside of the specification and show you a list where each of the different fields is represented as a column in that list. So this kind of opens the door for a whole bunch of new stuff. Most importantly, this opens the door for Janaga.net to start to generate these specifications and use this information.
And to connect to the Janaga.js server.
Yes, indeed. All right. So that's what I've been working on this week.
That's a lot of progress. And you only made one bug.
Yeah.
No, but that's very nice progress.
Yeah, for me, I was thinking something like recently I was thinking like using the graph to describe the memory and register usage in the program. So we can
Interesting.
maybe using a history modeling to describe how the program to use the memory, so we can try to like reordering some parts, since some parts is commutative.
Oh, right.
So yeah, so the reorder can make the concurrency or some speed up or parallelism.
Yeah. Right.
Yeah, so right, so
Yeah.
yeah, all this concept needs some background knowledge of the compiler, so I'm not so sure how the details I need to know. But yeah, so recently I was digging into this memory model issue.
Mm-hmm. Yeah, I was looking over
Yeah.
over here at my bookshelf. I know that I have a book that's all about compiler optimization, and yeah, the analysis of compiler optimization does go into some dependency analysis. So it figures out,
Yeah.
yeah, so it kind of draws a directed acyclic graph for what depends upon what. So yeah, I never really thought about it. Could that be modeled as a using historical modeling?
Yeah.
Yeah. So there's definitely, both of them are directed acyclic graphs, but hey, could one be modeled using the other? That is a really interesting idea, because then you could run the the interest calculation, and you could figure out okay, when this thing happens, these are the other things that need to change. So so this instruction happens, and then these are the registers that need to be loaded again, something like that. Yeah, there might be something to that.
Yeah. Also, do you remember like a few weeks ago I gave an idea like to cut the program into pieces.
Mhm.
So maybe with the modeling the memory model with graph can help us decide which place to cut the program.
Yes.
Maybe.
Yes. Yeah, I think so. Yeah. Yeah. That would be that's. You would want to figure out some heuristic of if I were to, so what's the cost of cutting it here versus cutting it there, and that cost is probably related to how many crossings you have. So if you've got some successors where their their predecessor edge crosses from one region to another, so I usually use those crossings in order to represent places in the model where different actors need to communicate. So one actor is responsible for creating these decisions, another one for creating those decisions, and so if one actor's decisions depend upon another actor's decisions, then that crosses from their region to another. And so that crossing means this one needs to publish a message that one consumes, so that it could figure out, okay, this is the thing I need to know. So yeah, that might be a different use for looking at those crossings. Is you want to define the region so that you break the problem down in such a way that reduces the crossings, because those represent the interactions. Those represent the points at which you need your program to block and wait for some other thing to finish, so that you could take that over. Yeah.
Yeah, good points. Yeah.
Yeah, that's
But
going to be
these
some
are just
research.
initiatives, so I think I need more time to bring out the details.
Mm-hmm. Yeah. Yeah, that's where the hard work happens.
Yeah.
Very good. Thanks, Caden. So, John, what have you got?
Let me show you first that small overview. That's where is it? Looking for that PNG here, Jinaga data structure. So this is back to the basics.
Mm-hmm.
But perhaps I will really understand it one day. So in .NET we declare a fact as a record.
Mm-hmm.
So then we can just make, for example, an airline fact in this way.
Yeah.
Now, is this what we call the runtime fact?
Yes. Yeah, that is the runtime fact because it's using the types that the application developer declares.
Okay. And what's the difference with the prototype?
Yeah, the prototype is an instance of the of a runtime fact. Actually, when you've got by the way, when you're editing a field like that, the only thing that shows up on the share is just that one cell. It's kind of interesting. So if you click out of that cell, we can see the whole thing again. Yeah. Thank you.
Yeah.
Okay. So so the so that line that you've got right there, it's not doing a JDOT fact. It's just saying new airline. So if you were to say JDOT fact, the new airline that you create.
This one.
Yeah.
This one.
Yeah.
Here?
There we go. That's the one. Yeah.
Yeah.
So the object created by new airline quote airline 1 is the prototype.
Okay.
Await JDOT fact returns a brand new instance. So what gets assigned to the airline variable is a runtime fact. It's just a brand new instance of the airline type.
Okay. And then what's the name for this one? Because here we really use the fact class.
Mm-hmm.
Where it is the internal format.
Yeah. I don't know that I have a consistent name for that. I think inside of the code I tend to call that idea fact, and then there's another idea that is fact reference. So this fact is a data structure that has a fact type, a hash, an array of predecessors, and an array of fields. Yeah.
Fields. Yeah.
So that's an application agnostic data structure that records all the information. So it's basically taken the runtime fact, done a bunch of reflection over it, pulled out all of the parts of that of that thing.
I have it here. So that's actually what the fact is.
Yeah.
So it has a fact reference. It has predecessors and fields.
Yeah. Yeah. There you go.
Yeah.
Yeah. So I was talking about the type and the hash. Those are grouped together to make the fact reference. Yeah.
So actually we can create a fact in two ways. One, either we make it a runtime fact, either we make it just a fact, and then we can switch from one to the other using the deserialize method.
Yes.
which is in the deserialize.test file, which takes.
Uh-oh. We lost him. Hey, it happened to me this time.
Oh.
Wow.
Yeah. That's progress. My problem solved. Your problem coming.
There we are.
So actually, the deserialize method, it takes in a graph because the graph is actually comparable with this instance. Yeah. Now this airline record just has an identifier in it, but it might have predecessors in it.
Yeah.
So actually, airline is a complete graph. It contains all the information, while this type of fact, it does not contain all the information. It contains an hash to a predecessor, but not the complete predecessor fact.
Right. That's correct. Yeah.
Yeah.
Yeah. So a predecessor is either predecessor single or predecessor multiple. In JavaScript, it's an array of objects or just an object, and then predecessor single contains just a fact reference. Predecessor multiple contains an array of fact references.
Yeah.
And a fact reference is just type and hash, nothing else. Yeah.
I have that one here. So fact
Yeah. There you go.
predecessor either just a single, either an immutable list of fact references.
Yes.
And it has just a role.
That's right. Yeah, I forgot the role. That's very important.
Yeah. But so that means actually this type of structure, the record, is equivalent to a graph. And that's why if we use the fact manager.serialize method,
Yep.
we convert the runtime fact to a graph.
Yes.
And not just to this type of fact. It becomes a full graph. And in the opposite way, we can have the deserialize method here, which takes in a graph and which gives out a runtime fact.
Yes. Exactly.
Okay.
Yeah, and you can see the
So-
second parameter there is the fact reference. So that fact reference is a type and a hash that appears inside of the graph. So it says, okay,
Yeah.
start from here, get all of its predecessors, and then give me the runtime fact.
And it will give the runtime fact with all its predecessors, the runtime fact that this fact reference points to.
Correct, yes.
And the successors that are still in the graph, they will be left out.
Correct, yeah.
Okay. Good.
Yep.
I started.
Yeah, you got
Perhaps
it.
I
You got it.
Good. Let's go then to another screen. Wait, no. Stop this streaming and then go to the screen. And then where is... So is that one not open? It should be. Oh, it's below. Make it a little bit smaller. Jinaga.net. So now you should see, yeah.
Yeah.
So if I go to, where is it here? SQL Store test. Okay. So two test methods. The first one, load nothing from store. That's the easiest one.
Yep.
You just make a new SQLite store. Let's
And call load with an empty list.
with an
Yep.
empty fact reference list, and it should be empty. And that one works fine. But then we load whatever from the store. What I did here, I just made all these runtime facts first.
Mm-hmm.
And the purpose was to create these facts in my database.
Mm-hmm.
Wait, no, here. So that's the
Yeah.
same way we did last time with await j.fact. And
Yeah.
so the facts are saved in the database.
Yep, with all the edges and ancestors and all that stuff. Yeah.
Yeah. And then my ID, and that's why I came to the overview that I just made, because that allows to be more clever. Then I created all the facts again,
Mm-hmm.
identical, using fact.create. The ID being that if a fact is identical, Jinaga will find out. So because I needed to load, for example, the passenger name tree, I needed a fact reference to that one.
Yes.
And I cannot get that fact reference here. So I created all my facts again.
Mm-hmm.
And then I could just load, where is it here? Passenger name fact3 dot reference.
Yeah, nice.
But I should be able to do it the other way around. If I use the fact manager.serialize method, and with passenger name tree, then it should give me the complete graph.
Yes, yeah, it should. Yeah,
And
because
then from
that has predecessors to passenger name 2 and 1, as well as the passenger all the way up.
Yeah.
Right.
And then I could take the last one, the topological.last,
Mm-hmm.
and that should give me a fact reference to this one.
Correct. Yeah, that should be the same fact reference. Yeah.
So, which means that all of this, all the way, yeah, I don't need it anymore. I can just replace it by fact manager dot serialize.
Yes.
I didn't
Yes.
try it yet, but
Yeah, so you would have to produce the graph, and producing the graph would require all of those intermediate facts to be expressed in this way. Yeah, and
yeah, but all these facts I have them here because they are passenger name tree is expressed in terms of passenger,
yeah,
and new passenger name, which points to my predecessors.
yeah. The thing is, that's a runtime fact, and the graph contains a
Yeah.
whole bunch of facts of application agnostic facts.
Mm-hmm.
So I think in order to build the graph, you would still end up having code very similar to that, if not exactly that code. I think so. If you take a look at the fact graph type, I think it's got a like an add method that
Where you can add facts.
yeah, and so I
Wait.
think it's
Wait. Let's try it.
yeah.
Let's try it
Let's
out.
give it a try.
So this one. So here I was thinking. So passenger. No, I just call it var graph
Mm-hmm.
equal to fact manager. No, new fact. Oh, it's not there.
Okay, right. Yeah, so yeah, you should be able to call serialize on the fact manager and give it the runtime
Yeah.
fact, and then it does all of that work. Yeah. So
Yeah,
it
but
might
my
be that fact manager
manager,
is not a public class. That might be what's happening.
I thought it was. Wait, do I have it somewhere here? No. Where's my, wait, go to Jinaga, go to my fact manager here. Jinaga managers. If there is no public, then it's private.
Correct. Yeah, it's private by default.
Yeah.
So we can make internals visible to the unit test.
Yeah, I did that with, wait, I tried that before. SQL store test. How did I do that?
Yeah, so that's done by an attribute in the code under test. So in Janaga, yeah, since you did that with SQL Store, you probably did that in janaga.store. Or janaga.store.sqlite. And so that would appear as an attribute. So in square brackets.
I think in my connection manager, no? Yeah. No. And what was that attribute? Do you remember?
Yeah. Let me look it up real quick. So .NET attribute internals visible to.
I did use it one time.
So in the this is a brand new feature of Discord. We've got chat inside of
Oh yeah.
voice channels. So yeah, in the chat for the book club, I just pasted the link to the internals visible to attribute.
Wait, how can I? No, that's not the one. Book club. Where is that the generals? No.
Yeah, if you hover over book club, you should now see a speech bubble that says open chat.
No. Oh,
No?
right click, it says open chat.
Okay, there you
go. Okay, internals visible attribute. This link will take you to, yeah. Takes me where? I should have used that somewhere here then. Where is he finding it? No, not here.
Yeah, this.
No, it was not. It was not that. Oh, yeah, perhaps. Was it not that you had to put it in? Parameter jinaga.test.
That yeah, okay, that looks like that is just an alternate way to define an assembly attribute. So yeah, you I'll often put them in code, so I'll have a code file that represents all of the assembly level attributes. But yeah, it looks like that's already set up that way. Okay, so it might just be a using. So the fact manager is in a different namespace that you probably just don't have a reference to inside of the test yet.
Wait, where was I? I was in my store test.
Yeah, so control dot, does it? Yeah, using Janagata managers. Okay, that was all it was. But yeah, for future reference, if you want to test an internal type or use an internal type in your test, there you go. Internal is visible too.
So new fact manager. Now I'm lost again. Here, serialize. That was what I wanted to do. And there I gave my passenger name 3.
Yeah. Okay, so yeah.
Oh, I had to give a store. Let's give it new SQL. Copy this one. Okay, that seems to work. So now I have that graph, and then I can say graph dot fact dot last. Last. No.
Yeah, I think it's just a property. Yeah.
That gives me a fact reference.
Yep. So that should be the fact reference of passenger name 3.
Yeah. So then I can comment out.
Yeah, that simplifies things quite a bit.
So comment, and so last ref. And then I just have to add in this one to here.
Yeah.
And of course, that test will still fail because for the moment, where is my load? There is almost nothing. So this is the empty case.
Gotcha. Yep.
and then I was playing a little bit with this, but I still have to. And finally, I will add my facts to my graph.
Yep.
And return the graph. One thing I was wondering here, in JavaScript, again, you were using, you were first loading all the fact IDs, and then you were making joins, but the result was a fact ID. No, there was also the name of the fact. Yeah, I remember. It was in the filter, because actually you came in here with a fact reference. The fact reference has name and has a hash code. The type name and the hash code. So why not directly filter in the SQL? Wait, it was in this one here.
Okay, yeah. I think the reason for that is to to rely upon the cache of fact type IDs.
Uh-oh.
Yeah. Hit both of us this time.
And now it was my turn.
Yeah. Yeah. So I think what I was doing there is relying upon the cache of fact type IDs in order to limit the number of joins that I need. But yeah, in order to produce the name I needed to have that join. Yeah, it seems like it would be
Because you
better
have
to just return the fact type ID and then go back to the cache in order to look up the name. That way you don't have to have the fact type join at all.
because you're only looking it up one time, so you would have to update your cache anyway.
Mm-hmm.
So I was thinking you might do it as well directly in the join,
Yeah.
but I might be overlooking something.
I think you're right there. Yeah, let me pull that up real quick. There's the Postgres store, and we're looking at load.
It's on line 230 and following.
Okay. So yeah, we load the fact types. Yeah, so this is looking through all the steps in order to get the fact types and then merging those in. Oh, okay. Yeah, that's because I added some stuff, so we're off.
The numbers are
yeah,
not
there's the
correct anymore.
specification. So yeah, here's the new code. Okay, so here's the load. Yeah, there's the big old query that's yeah. So
but that load, if you look to line 327, the fact types are loaded in there. Load fact types from references.
Yeah, so that one's.
And so that one goes to the database as well.
Yeah.
Connection factory.
Yeah, so we're just grabbing the type off of each reference, getting the distinct ones, and then yeah, so this is this is filtering out the ones that I already have, and then just fetching from the database the fact type IDs that I don't yet have. So if all of the types that I need are represented in there, then that will give me all the fact types I need. And so the question is here, why are we also selecting the type name? So we're doing this join again on fact type.
Yeah.
And I think this is a consequence of, you know what? I don't know. Okay. Yeah, so the references that I have here, these are the fact references of the leaves. These are the things that I'm trying to load. But I have no guarantee that that their predecessors' types are already in the cache. That's what it was, and so yeah, this list of fact references doesn't give me the types of their predecessors. If it did, then I could do a load fact types and make sure that that my cache is completely up to date, and then this fact type ID would be sufficient. Or alternatively, I could take this result with just the fact type IDs and verify that they're all inside of the cache, and then load that cache, load anything that's missing by fact type ID rather than by the fact name.
Okay.
Yeah, this could definitely be optimized.
I will have a look at it.
Yeah. But yep. Either by inferring all of the predecessor types, which in .NET you do have that information because it's all part of reflection. So either doing that up front, given all these fact references, or by doing that after the fact, by looking at the results and all of the fact type IDs in there. One of those two, you should be able to complete the cache just given the fact type IDs and be able to eliminate this join altogether. Yeah, you don't need T for anything else. Yeah, yeah. That would be good optimization. I like that.
Good. Let me see what I can make out of it.
Cool. Yeah, I would love to bring that optimization into Janaga.js.
That's about all I did this week. No, not all I did this week, but all I did for Janaga. Luckily, that was not all.
Very nice. Well, that's progress. We're inching up on it.
Yeah, it's going a little bit too slow on my side, but at least I start understanding it a little bit.
Yes, indeed. Well, excellent. So yeah, afraid we're a little bit over time, so I need to head in.
Yep.
But yeah, really enjoyed today's session. I think things are going to be moving forward a bit more quickly now that I'm able to get back into the code. So yeah, looking
That's
forward to
great.
the next time.
See each other next week then?
Yes, indeed.
Okay. Michael, see you. Caden, see you next week.
Thanks,
Bye-bye.
Thanks, Caden.
Okay, bye-bye.
Bye.